In this video, we're going to do an example where we calculate the integral on both sides of the divergence theorem in order to verify it for a specific example. The example we'll look at will have the vector field given by 2x plus y, x plus z, and then y minus 3z, and our surface is the cone z equals x squared plus y squared, and the top, which is given by the plane z equals 1. So that's the cone capped by that plane. So let's get a little sketch up of this surface and then we can parameterize the surface. So, like I said, it's the cone. You can think of that because if you hold your hand over the y part, you get z equals basically the absolute value of x, and the same thing if you hold your hand over the x part, you get z equals the absolute value of y. So this looks like it's opening in a flat way like the absolute value functions do, and then it opens circularly if you're looking down on it. Okay, great. So let's see, we've got this kind of picture right here. So that's our cone. Maybe we could call these sides here S1, and then we'll call the top S2. Let's go ahead and parameterize the side first, in other words, S1. And I want to do that by taking inspiration from spherical coordinates. And often, whenever we're wanting to parameterize these surfaces, you can take inspiration from some coordinate system, which is quite common, like spherical coordinates, cylindrical coordinates, so on and so forth. So as we'll see in this example, we'll parameterize one with inspirations from spherical coordinates and the other one being inspired by polar coordinates. So here we'll take spherical coordinates because we know that this cone has a really nice formula in spherical coordinates, and that is phi equals pi over 4. And you can see that because it's halfway between the positive z-axis and the xy plane. Okay, great. So spherical coordinates are given by rho cosine theta, sine phi, y equals rho sine theta, sine phi, and then finally z equals rho cosine phi. And like I said, if we set phi equal to pi over 4, that puts us right on top of that surface, or I should say right on the sides of that surface. So that is going to give us a rho, so that's going to give us x equals rho over root 2 times cosine theta. That's because sine of pi over 4 is 1 over root 2, or root 2 over 2 if you want to rationalize that denominator. That gives us y equals rho over root 2 sine theta. And then finally that gives us z equals rho over root 2, and then that's it. Great. But now we can actually simplify this quite a bit, and we can do that by making a slight change of variables, and this is also something you might want to do. After setting one of your parameters in your spherical coordinates or whatever equal to a number in order to get on a surface, you might want to simplify the parameters afterwards by making a change of variables. So here we might as well let u equal to rho over the square root of 2, because that ends up being inside of this all the time. And that's going to give us a nice parameterization in terms of u and theta. And that is going to be u cos theta, u sine theta, and then u. Great. And now you can check that if you plug this x, y, and z value into the cone, it actually satisfies that equation of that surface. So this is a parameterization. And now let's see what we need. We need u and theta to be on the cross product of the intervals 0, 1 cross 0 to 2 pi. So how do we see that? Well, the theta going from 0 to 2 pi is because you need to trace out this whole circle, which is making the cone. And then the u going from 0 to 1 is because notice our z component is exactly equal to u, but our z component needs to go from 0 to 1, given that the top of our cone is at the z equals 1 axis. Okay, great. So that's the parameterization. Now the next thing that we need is this ru cross r theta. So that plays the role of this normal vector in the surface integral. So that means we're going to need to calculate the cross product of these two partials. So let's see. If you take the partial with respect to u, we'll get cosine theta, sine theta, and then 1. If you take the partial derivative with respect to theta, we'll get minus u sine theta, u cosine theta, and then 0. Okay, great. But let's see what we get. So if we cross out the first column in the first row and then take that determinant, we'll get minus u cosine theta. Then if we do the same kind of thing for the second column in the first row, we'll get minus u sine theta. And then if we do the same kind of thing for the last column and the first row, we'll get u. Great. But if you see, this is actually pointing in the wrong direction. Notice that here, u is pointing, so notice here the z component is pointing up, and these are pointing inward. So this is actually an inward pointing normal vector, which is a problem because the divergence says that our surface needs to be oriented outward. But luckily we can change that just by taking, instead of ru cross r theta, we'll take r theta cross ru to be our normal vector. Recalling that when you change the order of a cross product, you just get a minus sign. So this is going to give us u cosine theta, u sine theta, and then minus u. And that will be an outward-facing normal from this S1. Okay, so that's what we need here. So the next thing we need to do is use this to plug into the formula for the surface integral. So I'll go ahead and clean up the board, and then we will move on from there. So on the last board, we built this parameterization for our cone out of inspiration by spherical coordinates, and then we calculated this ru cross r theta. And I should say, we took this to be r theta cross ru. We took the different ordering of this. And this parameterized this thing that we're calling S1, which, like I said, was the cone. Now we can go ahead and take the surface area over this. So the surface area over S1 of f dot ds, so that's going to be the integral from 0, 1, the integral from 0 to 2 pi. So we've got that iterated integral. Now we're going to take f, evaluate it on the surface, which means we're going to change all of the x values to this, all of the y values to this, and all of the z values to this. So that's going to give me twice u cosine theta plus u sine theta. So that's my first component. And then I have u cos theta minus u, that plus u. That's my second component. And now I have u sine theta minus 3u. That's my third component. Just to reiterate, this is equal to f, our vector field, evaluated on our surface. So FRUV. And now we need to dot that into this cross product. Again, this is built off of the formula for the surface integral, so check that out if you need to. So here we have u cos theta, u sine theta, and then finally minus u. And then we've chosen to do this in the d theta du order. Although, as you see here, we can switch the order pretty easily because we've got nice bounds of integration and stuff like that. Okay, so let's see what we get for this. So we'll have the integral from 0 to 1, the integral from 0 to 2 pi. Now we need to do this dot product carefully. Before we do that, let's just recall that this part was r theta cross ru. So our formula is f evaluated on the surface dot that thing that we formed from taking that cross product. Okay. So let's see what we get. We need to multiply this with this for the first part of our dot product, so that'll give us 2u squared cos squared theta, and then plus u squared sine theta cos theta. Great. So the next thing that we need to do is multiply this thing with this thing. So that's going to give us plus u squared cos theta sine theta, and then plus u squared sine theta. Okay, great. And then finally, we need to multiply that with that, and so that is going to give us minus u squared sine theta plus 3u squared. Great. And then we've chosen, like I said, to do this in the d theta du order. Okay. So now I'm actually going to skip a couple of steps here because they're quite straightforward, especially kind of at the end of a Calculus 3 class. This should be pretty easy. So first of all, we can see that this sign and this sign cancel. And then the next thing that we can see is when we take the antiderivative of sine times cosine, we'll do that with a u substitution. U equals sine, but notice sine evaluated at 0 and 2 pi both give us 0, so that means this portion of the integral and this portion of the integral go down to 0. So you can check all the details for that, but that should be pretty straightforward based on the fact where this lies kind of within a multivariable calculus class. So notice all that we're left with is this term right here and this term right here. So I'm going to go ahead and write that. So here we have the integral from 0 to 1, the integral from 0 to 2 pi, and now we have, I'm going to factor a u squared out of those, so we have u squared, 2 cosine squared theta plus 3, and then d theta du. But now notice that this is a function of u times a function of theta, so I can factor the integrals. This is going to be the integral from 0 to 1 of u squared du times an integral from 0 to 2 pi of the rest of that stuff d theta, but I want to rewrite that a little bit. I'll use the power reducing formula to rewrite that 2 cosine squared theta as 1 plus cosine 2 theta. Again, like this is a really common formula when we're doing these kind of triple integrals and surface integrals and stuff like that. So that's really useful to remember. Now we're going to combine that 1 with that 3 to give us 4 plus cosine 2 theta, and then d theta. Okay, great. Now the next thing to recall is that when we take the antiderivative of cosine, we're going to get sine. We'll actually have 1/2 sine 2 theta here, but we evaluate that at 2 pi and 0, and that's going to give us 0. So this whole thing zeroes out. And notice, it's easy to see what goes on here. The antiderivative of that, it's going to be u cubed over 3, evaluated at 1, gives us 1/3. And then here we have 4 times 2 pi, or 8 pi. So 1/3 times 8 pi gives us 8 pi over 3. Great. So our surface integral over the cone part of our surface gives us 8 pi over 3. Now we'll do the surface integral over the S2 part, in other words, the top of that cone. I'll clean up the board and we'll get to that. All right, on the previous board, we finished calculating the surface area over this S1, which is this cone part, not the plane on top, but the circular part on the sides, and we got that that was 8 pi over 3. So all that's left to do to calculate the surface integral over this whole closed surface is to calculate the surface integral of the top. So that would be the surface integral over S2, so that's what we'll fill in here. Okay, so the first thing that we need to do is parameterize this, but notice that this top is essentially the same thing as a disk, which we know how to parameterize down here in the plane. It's just that disk that's been lifted up. So we'll again, inspired by some sort of coordinate system, and in this case, we'll take inspiration from polar coordinates. And we'll do that to write r, u, theta. I'll take my distance from, it won't be the origin here, but it'll be the z-axis to be u, since we've already used r here. So notice this is going to be u cosine theta, u sine theta, and then comma 1. Again, notice u cosine theta, u sine theta is like polar coordinates happening down in the xy plane, but then we boost that up to the plane z equals 1 by setting the z part equal to 1. So that'll give us this disk up here. So just to reiterate, we're parameterizing this disk up here, being inspired by these polar coordinates. And now we can take u comma theta inside the cross product of the interval 0, 1 cross 0, 2 pi, kind of just like we did before. Okay, great. So now let's go ahead and calculate RU cross R theta. That's going to be an important part of this calculation like we had before. So that's going to be, we need this cross product. We'll use the determinant version again. So the derivative with respect to U is going to give us cos theta, sine theta, 0. The derivative with respect to theta is going to give us minus U sine theta, U cos theta, and then 0. Notice the last component is the only non-zero component because of those zeros right there. So we'll get that from crossing these out, and that will give us 0, 0, U. Now we want to make sure that's pointing outward, but outward is upward in this case because we're on this flat part of the top. And yeah, that's pointing upwards because U is always between 0 and 1, so that's always pointing up. So we're good to go there. Now we can go ahead and apply our formula. So the surface integral over S2 of f dot ds, that's going to be equal to the double integral, 0 to 2 pi, 0 to 1, I should say iterated integral because we know how to split it up. And then we have f evaluated on the surface, but I'm going to use the fact that I'm going to dot it into that to point out that the first two components don't matter at all. So I'm just going to put asterisks there. So like I said, those don't matter. And then comma, this z component evaluated on the surface. So we've got y minus 3z, but we'll take this as the y value and this is the z value. So that's going to be u sine theta minus 3. Great. Now we're going to dot that into 0, 0, u. And then we're doing this in the du d theta order. Okay, good. But, like I said, we didn't need these first two parts because we're dotting them into 0, so that doesn't even matter. All we need is this times that. So that's going to give us the integral from 0 to 2 pi, the integral from 0 to 1 of, let's see, we have u squared sine theta minus 3u du d theta. Okay. Let's go ahead and take that u antiderivative first. So that's going to give us an antiderivative, 0 to 2 pi integral of theta on the outside. And now we have u cubed over 3 sine theta minus 3 over 2 u squared. And then we need to evaluate this from u equals 0 to u equals 1, and then do a d theta integral. Okay, so I want to cheat a little bit again. I want to notice first off that in this case, once we get around to the theta integral, we're going to be integrating sine over a whole period, which makes this sine part 0 once we get around to the theta integral. So all we need to do is this in the end, which is going to be minus 3 halves. Notice if we plug 1 into that, and then the integral from 0 to 2 pi d theta. But now if we take the antiderivative of that and evaluate it at 2 pi, it's pretty easy to see that we get minus 3 pi. But now minus 3 pi is the same thing as minus 9 over 3, so this is minus pi over 3. So that is the total value of our surface integral. Okay, great. Let's go ahead and clean this up and then do the triple integral part. So now we're going to use the divergence theorem to turn this into a triple integral. So notice we just calculated this right-hand side. Doing the surface integral part is usually the harder part, so hopefully this is easier. Now we need to take the divergence of f and perform the triple integral over this solid region which is made up of the cone. So let's see what we get for that. So we'll have the triple integral over E, where E is that solid cone, of the divergence of f. But let's just notice that's what we get if we take this differential operator d by dx, d by dy, d by dz, and dot it into 2x plus y, x plus z, y minus 3z, and then we have dv. So in other words, we need to take the partial with respect to x of this first one, partial with respect to y of this one, partial with respect to z of this one. But those actually turn out to be quite straightforward. The partial with respect to x of this is just 2. Partial with respect to y of that is 0, so plus 0. The partial with respect to z of that is minus 3. So we've got something like that going on. But notice, that's exactly equal to negative the triple integral over e dv. But the triple integral over e dv is just going to be the volume of e. But you can look up the formula for the volume of a cone, and you'll see that the volume of a cone with this setup, in other words, a height of 1 and a radius of 1, is going to be pi over 3. So here we get minus pi over 3, which is exactly what we had up there. So that verifies the divergence theorem in this case. That's a good place to stop.